Hey everyone, in this highlight video we're going to discuss Lewis structures. I know Lewis structures are something you've seen before, but it's something that we should be very confident with. Remember that Lewis structures are a way or a type of structure that allows us to account for the electrons in the bonds of organic molecules. They could be non-organic molecules too, but in this case we'll be looking at organic molecules. So let's look at a couple of rules for Lewis structures. First off, we only look at valence electrons. And so what that means is if we're looking at atoms in the second row of the periodic table, then those atoms should have 8 electrons around them. We refer to this as an octet. And remember, when a second row element has 8 electrons around it, we say it has a noble gas configuration, which makes it more stable. The other atom that's important here is hydrogen, and because hydrogen is in the first row, it can only hold a maximum of 2 electrons. Here's a few steps to drawing Lewis structures. Okay? These are listed as they are in the textbook. I'm going to make one change in that I'm going to take number 2 and I'm going to put it up in front just because this is how I like to do it. So the first thing that we want to do when we have a molecular formula that we want to draw a Lewis structure of is that we want to determine or calculate the number of valence electrons. All right? We do that by looking at the position of those atoms in the periodic table. And I've just excised a little bit of the periodic table here to focus on what parts of the periodic table are going to be important to us. Okay, of course, hydrogen is important. Hydrogen is in almost all organic molecules. And then the most important part is going to be going around along the second row and then down the halogens. These are the most common atoms that we're going to see in organic molecules. We may also later see atoms like aluminum or silicon, phosphorus, sulfur, but we'll deal with that when we get there. So we want to remember the number of valence electrons for each of these atoms. So let's just start over here with hydrogen, right? Hydrogen has 1 valence electron. What about when we get to boron? Boron has 3. Carbon is 4, nitrogen 5, oxygen 6, and all of the halogens have 7 valence electrons. All right, so it's going to be important for you to know these atoms and know the order in which they are in the periodic table, because the order gives us the valence electron number, and it also allows us to understand trends like electronegativity, which are going to be important as well. All right, so after we've determined the number of valence electrons, we are going to arrange the atoms next to each other in the way that we think they're going to be bonded. Sometimes this might be obvious, other times I might have to give you a hint. Some other things to realize is that hydrogens and halogens are going to be on the outside of the molecules because both of those types of atoms only will have a single attachment point or a single bond. We will then use electron pairs to form bonds between those atoms, and then we'll count up the number of electrons around each of the atoms, and if they don't have complete octets already, we will add either lone pairs or non-bonding pairs of electrons or multiple bonds. All right, the final thing that we may have to do in some cases is if our structure has a charge, a plus or minus charge, then we're going to have to assign formal charges to those atoms. So let's try adding up the valence electrons on this problem. All right, so let's try structure. All right, so the first thing that we're going to do is to determine the number of valence electrons. Okay, so here we're going to just count up our valence electrons. We have 2 carbon atoms. Each of those carbon atoms has 4 electrons, so that gives us 8 valence electrons. we have 6 hydrogen atoms. Each of those atoms has 1, so that gives us 6 more. And we have 1 oxygen atom that brings in 6 valence electrons. We add these up, and we should have 20 valence electrons in our finished structure. So we have to be able to account for all of these electrons. All right, now step 2 here, I've rearranged those steps, is that we want to arrange the atoms next to each other in the order in which we think that they're going to be bonded. Okay? So we have 2 carbons and an oxygen, and those have to make the core portion of the molecule. So let's just attach them here. We have a carbon, and an oxygen. Okay? And so now we have 6 hydrogens that can go around these 3 atoms. So let's just start placing them over here around the carbon. I'm going to place 3 here, 2 here, and the final one I'm going to put over here on the oxygen. All right, as we do more and more of these, you're going to get used to the likely places to place those hydrogens. All right, so step 3, we're going to use electron pairs to form bonds. All right, so let's put an electron pair for each of these bonds. There's 1, there's 2, 3, 4, 5, 6, 7, 8. All right, we have 8 pairs of electrons. That gives us 16 electrons. So are we done? No, because we need to have 20 electrons, not 16. All right, so where do we put the other 4 electrons? So let's look at our structure. What we want to do is look for completed octets, and if we find an atom that does not have an octet, we're going to either use lone pairs or multiple bonds to give that an octet. All right, so let's look at the oxygen. Right, the oxygen has only 4 electrons around it, so if we put 2 more pairs of electrons around the oxygen, it now has a complete octet. All right, so all of the heavy atoms, the carbon, the non-hydrogen atoms, the carbons and oxygen, have octets. Each of the hydrogens have 2 electrons. So this molecule, this Lewis structure, looks good. All right, so there's another way that we can draw this structure, though. In this case, I've drawn all of the valence electrons as dots. So another way that's common is to draw each of the bonding pairs of electrons as a line. Okay? The important thing is that we just have to remember what these lines represent, right? Each of them is a pair of electrons. Okay, to complete our Lewis structure, we still have to put our non-bonding electrons on the oxygen. All right, so this is another type of Lewis structure, and this is what they use most commonly in the book. All right, this portion of the molecule, this OH, is called an alcohol. And this specific alcohol with 2 carbons is called ethanol. So this is the alcohol that's in alcoholic drinks like beer and wine and things like that. All right, so is this ethanol, is the structure of ethanol here the only way that we can put these atoms together into a good Lewis structure? Well, in fact, it's not the only way, right? So what if, instead of having the 2 carbons in a row, we put carbon, oxygen, carbon? All right? And now we can add our hydrogens around the carbons. And then we can add our electron pairs. First, we can add the bonding electron pairs as lines. And then we can finish off by the two lone pairs of electrons on the oxygen. All right, so this is a legitimate, good structure as well here. This type of group is not an alcohol. It doesn't have the OH, but this one is called an ether. An ether is a molecule that has an oxygen connected to two different carbons. All right, so this begs the question. We have two structures here. They both have the same molecular formula, but the structures are obviously different. One is an alcohol and one's an ether. So what is the relationship? What do we call the relationship between these two structures? Okay, these are called isomers. Okay, and isomers are molecules that have the same molecular formula, but they are different. Okay? If they're different, like these two are, in the order of bonding of the atoms, then they are called constitutional isomers. All right, and we'll see more of this when we focus in on how to draw organic molecules. Okay, so let's try one more problem. All right, so that molecule is called chloroform. It could be called chloromethane, but a common name is called chloroform. It used to be used as an inhalant anesthetic for... Okay, let's do two more examples here. All right, we're just going to work through here. Step 1, count up the valence electrons. Okay, we have 1 carbon, 4 electrons. We have 2 hydrogens. Each of those brings in 1, so we have 2 more. And then oxygen has 6. That gives us a total of 12 valence electrons. Okay? So now we're going to arrange the atoms next to each other in the order that we think they're bonded. Okay, so the carbon and the oxygen have to be bonded to each other. Carbon, oxygen. And then the question here is, where do we put the hydrogens? Okay, and you're going to gain a lot more experience on this, there could be a lot of trial and error, or sometimes I'll give you hints. All right, so on this one, what we're going to do is we're going to just start out by putting the 2 hydrogens on the carbon. All right, step 3, we're going to use lines for pairs of electrons to bond these together. So we have a bond between the carbon and the hydrogens, and a bond between the carbon and the oxygen. Okay, so how many electrons have we used up? We have 3 bonds. 2 times 3, we have 6 electrons. We need to place 6 more electrons on this molecule. All right, so what if we try just placing, let's just give this oxygen an octet. There, now the oxygen is good. So how does the structure look? Is it finished? No, look, the carbon now does not have an octet. All right, so it's not quite good. All right, so what we're going to do now is, the other thing we can do is create a multiple bond. So we're going to take one of the pairs of electrons on that oxygen, and we're going to move them down, and the oxygen and the carbon are going to share them. And we're going to end up with a new structure here that now has 2 bonds, 4 pairs of electrons in between the carbon and the oxygen. So we can draw our lines to the hydrogens, and then we have 2 pairs of electrons left over on the oxygen, And so now look at this. So the oxygen has 2 pairs of non-bonding and 2 pairs, it can count both of those, 2 pairs of bonding electrons. So it has 2, 4, 6, 8 electrons around it. The carbon has 2 pairs of bonding electrons to the hydrogens, and it has those 2 pairs going to the oxygen. So we can count all of those. So we can say both have octets. All right, so this is a good structure. This molecule has a common name. It's called formaldehyde. You may have smelled this molecule before if you ever worked in the biology lab around preserved specimens, preserved frogs, or did fetal pigs, or anything like that. So formaldehyde is oftentimes used as a preservative. All right? So this 2 lines together, this is referred to as a double bond. Okay, so formaldehyde has a carbon-oxygen double bond. All right, one more. This has just, look, we're getting less and less atoms here. Well, the same as over there. We have, going to do our valence electrons. We have 2 carbons. Okay, 2 times 4, that gives us 8. And we have 2 hydrogens, gives us 2 more. This molecule will just have 10 valence electrons. Okay? We're going to put the 2 carbons next to each other. Right? And let's just make this symmetrical. Let's put a hydrogen on each end. All right? We're going to link these together by bonds or by pairs of electrons. So we have 2, 4, 6. We have 4 more electrons that we have to place in the molecule. Here's 1 pair, so that's 2. Let's just put the other pair on this carbon here. All right, so how does this structure look? Now, it's not that great still yet, right? Because both of those carbons only have 6 electrons around them, right? We want to have them both to have octets. All right, so we're going to move this pair of electrons in between to make another bond, and we're going to move this pair in there as well. So in this structure, between the 2 carbons, we're going to have 3 pairs of electrons. All right, and we have the 2 electrons going to each hydrogen. Okay, this is referred to as a triple bond. All right, and this molecule, its common name, we'll learn how to name them all in a special way, systematic way later, is called acetylene. Okay, this is a gas, and it's used commonly in welding. All right, one more difference in this example is that our molecule here has a charge. Okay, so it has a minus charge. But we're going to start out following the same procedures we've been using up to now. So let's count up the valence electrons. There's 1 carbon, has 4. 3 hydrogens, 3 oxygen has how many? Has 6. And we have that minus charge there. So what do we do about that? Okay, the minus charge means that there's 1 extra electron on this molecule. All right? And so we have to, for the minus charge, we have to add 1 extra electron. Okay, so what's the total here? We have 4, 7, 13, 14. We have 14 electrons. All right, so let's follow the same thing we've been doing. We have a carbon and an oxygen, so those are going to be next to each other. And we have 3 hydrogens, and we're going to place all 3 of these around the carbon. We're going to put our bonds in, and then we have to see how many electrons we have. 2, 4, 6, 8 electrons so far. We have to place 6 more. Oxygen already has an octet, see? So the only place we can place these is around the oxygen. Okay, so now the carbon has 8 around it, the oxygen has 8, and everything's good. All right, but the last thing we have to do is this minus charge, we have to make sure where that minus charge goes, what atom it's associated with. Okay, so we have to assign formal charges. So here's the equation down here for calculating formal charge. So what we're going to do in this equation, we're going to take the number of valence electrons that we started out with for that atom. Okay, so for example, for carbon, the valence is 4. We're going to subtract from that the number of electrons that that atom has associated with it in this structure. And the two possibilities is that it could have non-bonding electrons, okay? Those non-bonding electrons aren't shared with any other atom, so it gets to count all of those. And it has bonding electrons, and it gets to count only half of the bonding electrons because it's sharing those. All right? And we compare those two. If it has more electrons associated with it than it had valence, then it's going to have a minus charge. If it has less than its valence, it has a plus charge. All right, so let's calculate the formal charge of this carbon. Okay, so we say the formal charge equals the number of valence electrons equals 4. Subtract from this the total number of electrons that are associated with that carbon. All right, so does it have any non-bonding electrons? No, it has 0 non-bonding electrons. It has 8 bonding electrons, but we divide that by 2. So we have 4 minus 4 equals 0. All right, so that carbon is neutral. All right, so we already know now where the minus charge is, but let's work on the formal charge calculation here to make sure. So the formal charge equals the valence, right, which was 6, minus the total number of non-bonding electrons, 2, 4, 6 non-bonding electrons. We add to that half the number of bonding electrons. There's only one bond to the oxygen, so that's 2 electrons. We divide it by 2. We have 6 minus 6 plus 1 minus 7 equals minus 1. Okay, so it's the oxygen that has the minus charge. All right, so here, try another problem calculating the formal charge. All right, let's summarize what we've learned or what we might have observed about different bonding situations for these atoms on the second row of the periodic table. All right, so we'll start out with carbon. Carbon is the most important organic molecule. All right, not molecule, but atom. It's the basis for organic chemistry. All right, so we start out with the number of valence electrons. So carbon has 4 valence electrons. All right, so let's draw out a carbon with 4 electrons around it. All right, let's just put 4 unpaired electrons. So if you look at that, how many bonds do you think carbon can make? All right, well, it can accept an electron at each of those unpaired electrons to make pairs. All right, so because it only has 4 electrons, carbon likes to make 4 bonds, okay, if it's going to be neutral. So all of these are for neutral structures. All right, carbon cannot make more than 4 bonds. All right, so let's look at the possibilities of 4 bonds, okay. You can either have 4 single bonds like this. It could have 2 single bonds and a double bond. It could have 2 double bonds. Okay, this is more uncommon, but it's possible. Or a carbon can have a single bond and a triple bond. All right, so what we want to be able to do is look at any molecule, and if we see any of these situations, we'll know that that carbon is neutral. All right? All right, what about nitrogen? Okay, how many valence does nitrogen have? Okay, nitrogen is right next to carbon. It has 5 valence electrons. Okay, let's draw the nitrogen out. Here's 1, 2, 3, 4, 5. All right, so how many bonds can nitrogen make? Well, it has only 3 unpaired electrons, so nitrogen, neutral nitrogen, likes to make 3 bonds. Okay, the possibilities are 3 single bonds with a non-bonding pair of electrons, a single bond and a double bond with a non-bonding pair of electrons, or a pair of non-bonding electrons and a triple bond. Okay, so each of these situations, the nitrogen has 3 bonds. Okay, oxygen's next. Oxygen has 6 valence electrons. We'll draw this out. That means it has only 2 unpaired electrons. That means that oxygen likes to make two bonds. Right? We've seen these so far. We could have 2 single bonds like this. Okay, that's what we saw in the alcohol, in ethanol, and the ether. Or oxygen can have a double bond with 2 non-bonding pairs, and that's what we saw in formaldehyde. All right, so these are the possibilities. For hydrogen and halogens, let's look at these. Hydrogen has 1 valence like this, so it can only make 1 single bond. And halogens, I'm going to abbreviate it with an X. That's a common abbreviation for halogens. How many electrons, valence? Has 7. Right? See, it has 3 pairs and 1 unpaired electrons, a paired electron, and so halogens, neutral halogens, typically make 1 single bond. All right, so these are all the neutral molecules. All right, so let's quickly finish off here by looking at what possibilities there are if these atoms could have a charge. All right, for carbon, there's really 2 possibilities. Okay, we can either have carbon with just 3 electrons around it, or we can have carbon with 3 bonds around it. I meant 3 pairs of bonding electrons and a pair of electrons like this. All right, so what do we think? If we have only 3 bonds around it, only 6 electrons, then this ends up with a plus charge. You could work out the formal charge calculation. This is a carbocation, right? Cations are positively charged species. And the one with 2 charges has a minus charge. This is called a carbanion. Okay, both of these we will see as reactive intermediates, but they're not neutral compounds. For nitrogen, the most common is nitrogen that has 4 bonds. So essentially the non-bonding pair that I showed in all of those ones over to the left has been used to form another bond. So essentially it's given away 1 electron in the process, and so this has a plus charge. This is called the ammonium ion. Oxygen can have either a minus charge or a positive charge. All right, we've seen these before, but if oxygen has, we actually did an example like this, 1 single bond and 3 pairs of electrons, it has a negative charge. If that bond was going to hydrogen, this would be just hydroxide. All right. In order for oxygen to have a positive charge, it will have 3 bonds and 1 non-bonding pair of electrons. Okay, this would be a plus, could also have a double bond and a single bond. This would be a plus, like that. All right, so we see these kind of examples as we move forward. For hydrogen, hydrogen has two charged species. We have either a proton, right? Remember, a hydrogen atom has one electron and one proton, so if we take away that electron, we have only a proton left over. Or if a hydrogen has two electrons, it has a minus charge. This is referred to as hydride. For halogens, we typically see just a halogen with 8 electrons around it, so a full octet. This would be a minus charge. This would be called a halide. Oops. Like chloride or bromide or fluoride. Or we will see situations where this X could have 2 bonds like this, and then it would be a plus charge. Okay, this is less stable because halogens tend to be more electronegative. They don't like to have that plus charge. Okay, so this is a big summary. So what we'd like to accomplish here is a level of comfort with these types of structures. So if we see a certain structure, we know if there's a charge. We know if it's neutral. We don't have to go through and calculate a formal charge for every atom.